All right.
Yeah, no, it was like the two couple, Linda and Linda.
That's nice. Let's get going here. So I have a capacitor. It's two metal plates that are stacked on top of each other. What happens when I change the value? First thought, I have a gap. Max, what happens?
There's no current running through it.
Should be no current.
Maybe no.
Yet if I put an ammeter right here in my path, there would be current. So how do you get current? What is going on? The answer to the question is the electrons sensing that, hey, look, I have this big old metal plate here that I can hide on instead of hanging out in the battery. The electrons start to pile up on this side. And when the electrons start to pile up on this side, because they can spread out more, on the other side, the electrons do what? I don't want any part of it. There's a negative thing forming over there, which makes this side over here positive and makes this side negative as the electrons go. And so for a while, you have current. Why do I say for a while?
It runs out when the battery runs out.
Nope, the battery can run this forever. Let's say I've got a power supply, I've got a generator, I'm running. It'll eventually stop running current.
Lose a lot.
Nope, not going to hop. How so?
The forces that are pushing them away are
not going to be any more electrons on the other side. Push them all away.
Well, we are. And in addition to that, I mean, you're asking electrons to pile on plates with other electrons, right? At some point, that becomes the voltage here is not sufficient to push them on there anymore. Okay? Their desire to get out of this battery is not going to be enough to get them on that plate. If there's enough electrons in this plate. Okay? And since these electrons are driving electrons off of this plate, you end up with the charges on this, plus Q, negative Q, and in normal situations are going to have the same charge. And the gap in between them is going to have nothing going through it. Now, we call this item a capacitor because if I take a voltage, hold on, don't look at this part. Okay, so that's what. Okay, good. So this is the equation I'm trying not to show you guys because I mess people up every year by showing everybody that equation. It's not actually on your formula sheet. It's my way of looking at the universe, not your way of looking at things.
It's like the key to all of this.
It is the key to all this. It is. It's the key to all this, and yet that's not the way you guys should learn how to do it. All right, so C equals Q of A. So what happens is, the larger the voltage, the more charge I can store on this capacitor. But also, the geometry and the metal and the gap in between determines how much can be stored per volt. And so capacitance is the amount of charge that can be stored per volt. And so my formula is capacitance is Q per volt, or charge per volt.
Whoa.
Yes, sir.
Does it eventually release this charge?
How would it?
Touching on the other?
Aha! So in the back of your TV, if you look carefully at the back of your TV, even a modern TV, it says on there, do not open this. I don't care if it's unplugged, don't open this. And you might wonder, well, why not? Because that seems dumb. If I've got it unplugged, it says electrocution hazard. It's unplugged. How could I possibly be electrocuted by this thing? So what you do is you pop that sucker open, you look around inside, you'll find there's two metal plates in there that drive the whole system. That capacitance allows it to accelerate electrons up, and we'll talk about that a little bit more later. It also, but when you think about electric field between these two, right? The two metal plates, you have electric field, right? So you can really cause an electron to fly off this thing, right? Yeah. And so if you have this thing charged, it allows electrons to have different energy levels, which corresponds to different colors on your TV. A little trickier on a more modern TV, but it still works the same way. They just have to go through a couple more devices to make that work. That, in order for that to work, though, that has to be charged about 10,000 volts. And you have to have a lot of electrons, a lot of charge. So when you pop that open, that back, And you go, huh, what's this thing here? Well, suddenly you've given it the ability to start transferring charge from here to that spot over there, right? And so all of this stuff is going to instantaneously decide to go through your finger, which would cause a smell of fire, and you get to go to a trip to the hospital if somebody finds your body. If they don't find your body quick enough, you're not going to the hospital, you're going to another place where they burn your body and stick you in a hole in the ground.
Really? We open our heart?
No, we're not going to do that. I don't want any part of it.
Even LED TVs, like I understand that for CRT or whatever.
Yeah, LED TVs have a capacitor in them. I honestly don't know how big it is. It has to have one in there. I just don't know how big it is, so I can't tell you for sure it'll fry you and kill you. I mean, I suspect if you look at the back of your TV, it'll tell you the answer to the question. Yeah.
Why on old type monitors, if you left something, the same thing on the screen? So
Oh, it was like
why is there an imprint?
Oh yeah.
Well, if you mean the permanent imprint is from the fact that you've got electrons. You're firing electrons at that screen through the plasma and the back of the screen at that screen constantly for however long that is. That's energy. That's heat, and you're burning it into the system. You actually, when you say you're burning your screen, you are actually burning your screen. You're melting it permanently in your screen. Now, there are what's called magnetic phantoms, which is a more colorized version. In a more colorized version, what's happening there is you screwed up the bulb behind there, and you've changed the way the glass's atoms are changed, which causes a permanent color. That's because you're messing with the magnetic fields that are around. You do the same thing by taking a magnet to the TV set. Walker.
No, I'm doing that too. We need a new TV.
That's how we got the TV we have today. Walker took a big magnet on the TV. And you can see all the electrons curving. It was the coolest demo for like 2.2 seconds. And then after that, the TV didn't work so goodly.
Didn't they take some credit card that we had?
We've done all sorts of things.
Card
You put the credit card into the thing at the bottom. That fried out our cable box. All right, moving on.
Techie things.
Yeah, techie things. All right, so this is that. So now the question is, the basic formula is this. You got this basic formula here, okay? And then it says, we'll do basic formula. Let's go back to the basic. That's basic formula. I need another one, don't I? I need another basic formula, or do I have capacitor someplace else? I'm kind of confused here. Capacitor wrap up. I used to put this in the front. That's why this is confusing to me. Yep, I explained it there. So that's good. I don't even need that. That's cool. All right, so let's talk about what happens when I put these in a circuit. Okay? If I put them in a circuit, something interesting happens. If I have a voltage here, let me back up. When this thing reaches the same voltage as this, but opposite direction, that's when current stops flowing. Okay, that was the idea. Voltage controls this. So if this voltage ever gets up, this is 10 volts. When this gets to 10 volts, that's when current stops flowing in the wire. Okay? And then if you pop off the battery and put a resistor on there, you get 10 volts for a moment coming out of that capacitor. And it'll slowly keel down, right? And slowly the voltage will go down as electrons go. So the only reason they have voltage at all is because the electrons stuck on these plates. Once they start leaving the plates, you lose the voltage. Yes, sir?
How do capacitors in our electronics? There's no moving parts. How does that work? Those little circular water tank guys.
Yes. Well, first of all, capacitor is a circular water tank. I'm not going to answer your question because I don't yet understand it. But what they do is they take the two plates like this, and they just curl it.
Oh.
Just enough.
The whole point of a capacitor is that you charge it up and
Charge
it
it.
releases all that charge.
And then it can release a charge all at once at some later date when you attach it in a different way. Yes.
How does the capacitors that we have?
Usually you have an IC circuit. IC circuits have switches inside them. And it's a physical switch. It actually clicks. If you listen to an IC circuit on the non-high speed sort of one, because the high speed you're not going to hear it, but you can actually listen to it. You can hear it click because they're switching which way the current's going. All right. More on that maybe much later. So we've got everything set. So what happens when I have two of these? I've got this all messed up. What happens when I have two of these in parallel? Specifically, what does a capacitor do? A capacitor stores charge. Can I store more charge, less charge? What happens when they're in parallel? More charge, why? And more electron spaces to hang out, right? So what happens is this. If this is 10 volts, and this is going to be 10 volts, and this is going to be 10 volts, because charge is going to flow until they get there, right? Because of that, each one of these acts individually as a capacitor, which means your total capacitance would be equal to C1 equals, total capacitance would be equal to C1 plus C2 plus however many you have, right?
Let me guess this last one.
It's coming. You can feel it.
What's coming?
You can feel it. Here it comes.
Why is it joules per flamingo? What's that?
I haven't talked about what a flamingo is yet.
That's right.
He's trying to read ahead.
Oh.
We'll talk about what a flamingo is in a moment. All right. Now, what happens when they're in parallel? When they're in series. We all feel like that's what it's going to be, right? Can we explain why? Just because, other than the fact it feels like that's what it has to be. I mean, that is the answer. Let's go ahead and call it what it is, and let's say that this is the best way to remember it. It's the reverse, right? Series, you get the parallel formula. Parallel, you get series formula. It's a reverse of a resistor. Ooh, that's an easy way to remember it. Better question. Why? Why?
Nobody.
Who cares? The universe cares.
Wait, why would anyone ever do capacitance in a parallel or
Trust me, these all happen in real life.
How would they do a series? That makes no sense. Why don't you just make a little
less storage, but it would allow me to have, if I have switching systems, I can actually draw from each one of them individually and power them from one supply. So I can have a whole set of capacitors charged, and at the end I can pull off the different pieces. Solid. Okay, moving forward. This situation here, why does it have less? Because, and this is important, this idea here is going to bail you out when things get confusing, so listen. When it's not charged, where are all the electrons? I've got my electrons here, start to go here, they start to charge this plate. The electrons flee here. How far can they go? They can only go to here. And then electrons flee here and go back. Which means that the electrons here, these two plates, have to have the same charge. Which is another property of when they're in series. These two plates have the same charge, because whatever comes off this plate goes onto that plate, and that's all that can happen.
Oh, that's a good point. So, but how close do they have to be together if they're not the same charge?
Doesn't matter. As long as there's a wire between them, they can be way far apart.
Really?
Oh, yeah, way far apart.
In real life?
Real life, way far apart.
Like a mile.
Yeah, farther. Way farther.
Really?
They've used capacitance systems over the continental United States.
The actual electron is still on the plate. How can it reach out that far?
Because they bump this guy bumps this guy, bumps off into here. How do you get power to your house?
What?
How do you get power to your house? Electron from the power plant hits the one in front of it and gets all the way, the chain reaction lands in our house and runs our dishwasher.
So it's like a tube and marbles?
Yes.
Is NV
Same thing. All right, so positive, negative. So these have the same charge. If these have the same charge, it means the capacitors have the same charge. The capacitors have the same charge, which means the voltage cannot be used to drive just one of these. It has to drive both of them. And so there's a voltage drop across each of them, just like we did in series circuits. There has to be a voltage drop across each. The voltage drop? Not necessarily. It depends on the capacitor. If one's a small capacitor, it takes more volts to get the same charge in it than this one, right?
The plate and battery little icons look.
They're a little too close, aren't they?
Yeah.
It's a little annoying.
So I'm probably going
All right.
to answer.
All right. So with that in mind, oh Lord, we're running out of juice here time-wise. Oh,
I will